Well, hello everybody again. Again, we will go directly to the Poisson distribution since we finished the previous lectures that talking about the binomial distribution and we discussed the factorial and the other things. Now we'll go directly to the Poisson distribution, and I hope that you can get something from it. Actually, I wish you all the best in the corona infection, and hoping all of you to be in good health. Be careful and avoid everything that can cause this infection for you, for all of you. Poisson distribution, as we see here, it's a discrete distribution that have been developed by a French mathematician. His name is Simon Poisson. So from this, from the nomination from this for this distribution, it came from the mathematician who discovered this thing, and he lived for about 59 years, born at 1781, and he passed away 1840. So he is a French mathematician. He developed this distribution, and we do need to start talking about it. The general formula for it, or the general discussion behind this distribution, we can say if x is a number of occurrence of some random event in an interval of time or space or some volume of matter, the probability that x will occur is given by this formula. This formula is the Poisson distribution that gives us the probability of occurrence if x equal to e to the power of minus lambda times lambda to the power of x over x factorial. And we know from the previous chapter how can we deal with x factorial and the theories behind this formula. And here lambda is called the parameter of distribution and is the average number of occurrence of the random event in interval. So lambda is a parameter, is the parameter of distribution, and is the average number of occurrence of the random event in an interval or volume. So, and the simple E here is a constant number, which is 2.7138. This is a constant number. You can use it directly. Just add 2.7138 instead of E and give it the power of minus lambda. And lambda here is the parameter of distribution. Just use it as it is in this equation. It can be shown that from this distribution, as we discussed earlier, that the probabilities are the same. They have the same characteristics, which is the fx should be more than or equal to 0. It cannot be minus or more than 1, because the total number of the summation of all fx's here should be equal to 1. Should be equal to 1. So return back to the binomial distribution, return back to the distribution and the probabilities, cumulative probabilities, relative probabilities, relative probabilities. You can see they have what we call the same characteristics, which are greater than or equal to 0, and the summation of all those probabilities should be equal to 1. So that the distribution satisfies the requirement for probability distribution. So the Poisson process here, as you see, it is this statement describes what is known as the Poisson distribution. The following statements are Poisson distribution. The first one is the occurrence of the event are independent. The second one is an infinite number of occurrence of the event must be possible in the interval, and also the probability of the single occurrence of the event in a given interval is proportional to the length of the interval. So we have intervals and we have what we call probabilities. The single occurrence of the event given in an interval, okay, should be proportion of the length of the interval. So we are dealing with intervals, and we are dealing also with the probabilities within this interval. The fourth statement here, in any in any infinitesimally small portion of the interval, the probability of more than one occurrence of the event is negligible. So this is negligible. It is a very good statement that to be addressed here. So the mean and the variance of the Poisson distribution are equal. This is the main statement that should be known for all of you. You do need to know it. The mean and the variance of the Poisson distribution are equal. We do need to differentiate between this Poisson distribution and the other distribution that discussed early and will be discussed in the future. Means and the variance of the Poisson distribution are equal. They are the same. When to use the Poisson model? When we are aiming to use it. In which cases can we use the Poisson distribution or model? A Poisson distribution used when counts are made of events or entities that are distributed at a random in space of time. So this is the first thing to be known. The Poisson distribution used when a count. So when we have any events that needs count, okay, or entities, as we see right here, that are distributed in a randomly in space or time. So the randomness here also should be suggested. Because we do need to give them all the events the same probability for being chosen. We don't want to be biased to concentrate on a certain events and ignore the others. So the randomly at a random in space or time. So this one is this component of this sentence give us this paragraph actually give us counts. We do need to see counts to be made or event or entities. So we have counts عدد بمعنى آخر of events or entities that are distributed in randomly in space or time. For example, in suicides study, researchers found that the monthly distribution of adolescent suicides in a specific country between 1977 and 1987 closely followed the Poisson distribution with parameter lambda equal to 2.75. Find the probability that a randomly selected month will be one in which 3 adolescent suicide occurred. This is the main example. So here we do need to we have a count, okay? So we have count right here, and from this count we have an event. So this is a Poisson distribution. This is followed by, in this statement we refer and we indicate that this thing is followed a Poisson distribution. It's obviously, we don't need to think about it because it's there. It's a Poisson. We write it here in this example as a Poisson distribution. So this example is dealt with suicides. Okay, some researcher returned back in the history looking for suicide study. They conduct a suicide study. Okay, in monthly basis. This in monthly basis deals with what? With adolescent suicides. So this study conducted between 1977 and 1987. So it's a time period. It's a time interval. And here we indicate again it's a Poisson distribution. The question here, and we assume the lambda here is equal to 2.75. We give it in the example. So find the probability that a randomly selected month between 1977 and 1987 will be one in which 3 adolescent suicide occurs. This is the main question and the main example. So the solution for it, just apply the equation that we previously discussed. Okay, fx equal to e to the power of minus 2.75 times 2.75 to the power of 3, because the adolescent here is 3. Okay, 3x over or divided by 3 factorial. So by applying this equation, or applying for this equation, and do the mathematician as we previously indicate that E is a constant. So you return back to the previous slide, you can find E is the constant, the number of the value of the E, and give it its power minus 2.75 as lambda, and 2.75 is a lambda here, and the 3 again. 3 is in our question in a selected month will be one in which 3 adolescent suicides occurs. So it will be 0. The final result is 0.221584. Again, factorial here is 3. How can we get 6? Because we will multiply 3 times 2 times 1. So 3 multiplied by 2 will be yield 6. 6 multiplied by 1 will be 6. And this is 6 in the denominator. And the denominator, just apply the equation and put all the values that you have in your example.